left their clicker here last time? Does anyone recall leaving their clicker here? Well, take out your clicker and see if you find it. And vote. Vote early, vote often. Anybody notice their clicker is missing? I guess we should be able to track it down, but maybe it's not from this class. Okay, let's just start with some basic votes here. Vote number 1: are you here? Yes. Or we can make it a little more interesting. Are you alert and engaged? Are you B, not alert and engaged, but still here? This projector stinks, right?
Yeah. Yeah. I don't know. I'm trying. You can't see it.
Where's the remote for the projector? Does anybody see it? The remote for the projector is missing. Very good. Okay, who's good at projectors? Who likes to play with these things? Why during class? Any volunteers?
What do you have to do?
To try and make it so we can see the blue over there.
Might just be because those are still up.
Okay, let's put those down over there. I still think so. Anybody want to play with it? Going once. Okay. Okay, how many MATLAB lessons are there in those 2 tutorial groups? It's a total of 8, is it? 11. Okay, let's see where you guys are at. How many people have done all 11? How many people have done 9 or less? How many have done 7 or less, 5 or less, 3 or less? Completed all 11. You've done 9 or less, 7 or less. But what if you've completed? This is very tough. Okay, this is a bad election. Okay, you've completed all 11. You've done 10 or less, 8 or less, 6 or less, 4 or less. Completed all 11. You've done 10 or less, 8 or less, 6 or less.
Is that good?
That's much better. I don't know whether you did it or the shades did it, but it's much better.
All right, I'll put it back there.
Now, cancel this. New vote. Who is putting in all the time that you're asked to put in or more? And who is putting in less than that? Okay, so that means the lessons are going slow. Okay, another vote. Who would like just an extra, like Saturday help session in MATLAB, where you can just ask questions and do stuff like that? All in favor of some extra Saturday MATLAB help session? A. All opposed? Well, no, you don't have to be opposed. You're just not interested in it. A means you'd be interested in it. Okay? Okay. Let me move on then with today's class. So this week's homework, the one that you have to do Thursday, is just MATLAB and a short assignment from Professor Volker, which is really pretty easy. So don't be intimidated by the complicated drawing. It's an easy assignment. Who's done the assignment? How long did it take you?
30 minutes.
30 minutes, right. It's not that big a deal. Okay. We were working on hydrostatics. Hydrostatics is a special simple case of fluid mechanics as part of engineering. In developing the subject of hydrostatics, we used various reasonings of a type which you will see again and again. And I would recommend that you try, if you haven't got it yet, to understand the derivations that I did in lecture and that you were asked to hand in for homework. Part of the homework, which was meant to be a challenge, which is the one that you handed in last Thursday, right? or was it the week before? Last Thursday was this buoyancy problem. Even if you understood Archimedes' principle totally, you had this problem of figuring out how high this sphere would float in milk and oil, and you knew the density of the milk, you knew the density of the oil, you knew the mass of the sphere, or the density of the sphere. And what you figure out is that, according to Archimedes' principle, this sphere has to displace its weight of fluid. Now the thing is, this is up here, it's displacing all oil, that's not enough weight, so it would sink. If it was down here, the displaced milk weighs more than the wooden ball, and it would float, and it has to find an in-between place. It has to find an in-between place where the volume of milk displaced times its density plus the volume of oil displaced times its density equals the weight of the sphere, which is the volume of the sphere times its density. Yes?
That's supposed to be 4 pi r3?
Yes. So I will, as you've noticed, make lots of errors of this type, and you should not hesitate to,
So you just have 2 pi's though.
as I said, I will make lots of errors of this type, and you should just correct them quickly and casually. Don't be worried about it. Well, in order to do this calculation, you have to be able to calculate. If you want to just say, oh, what fraction of the ball, volume-wise, is above and below, it's a simple calculation. If you want to calculate how high the ball goes up and down, you have to know the volume of the ball as a function of height. So it's my intention that you would try to work that out and then figure out how high the ball floats, which in the end means you have to find the roots of a cubic equation, which is another puzzle. So there's a whole sequence of puzzles in this puzzle. Some of you got a hint from the TA, which was a formula for the volume of a partially filled sphere, but I did not want you to use that, actually. I wanted you to try to figure it out, which I am now going to try to do. So what I'd like to do is a couple different ways work on figuring out the volume of a partially filled sphere. And the way I'm going to do that is, just because it's easier for me to draw things right side up and upside down, I'm only going to worry about finding the volume of a half sphere up to some height h. And if I can figure that out, then I can figure out the volume of a partially filled sphere, because I can add back in the other half of the volume. Okay, so how do we go about figuring that out? Well, we could try to remember formulas from here and there. And in the end, of course, you have to remember some formula. So there's some, like, what's the area of a circle? That's the formula. I'll just accept that we remember that. We could try to derive that too, but let's skip that. But you remember, say, the area of a circle. You remember some other simple things. But you'd certainly, I'd be willing to bet, nobody knew without looking up or calculating the volume of a partially filled sphere. So we have to build that up from things that we know. So how are we going to go about doing that is we're going to look at, I think I can just skip this for a while. We're going to look at this sphere, and we're going to try to calculate its volume up to some point. So we're going to try and figure out the volume up to some point like this. And we're going to assume this sphere has some radius, r. Now, we could make our life simpler and say the radius was 1, and know that we have to scale everything by r cubed. And I don't know which way I'll go with that in this lecture right now. So we want to figure out the volume of something like this. If we want to draw a perspective view of that thing, it's got a top like this. It's coming down like this. It's got a bottom like this. It's something like this at the bottom. We've got axes here. We could draw axes out like this. So this could be, say, x and y and z like that. And we're trying to find the volume of a thing like that. And just some hints for drawing. You saw that I have no talent at drawing, but bit by bit I've learned how to make somewhat intelligible drawings, and there's some tricks, like hidden lines should be dotted. Where one line passes in front of another line in 3D, put a gap in the back line. It makes it much easier to look at. When one line passes through a surface, put a dot. where two lines aren't just crossing, but are not passing one in front of the other, but they actually cross each other, put a dot. Okay, so we want to figure out the volume of that thing. So how are we going to figure it out? Well, in your calculus class, 191 now, you're learning, and if you're in 192, you learned this before, they have methods for this. The method of shells, and the method of disks, and the method of, I don't know, there's disks, cylinders, shells, whatever it is. And I would actually like that you do not think of this problem as one where you learn the method of shells, disks, cylinders, whatever, but that you can actually reason it out sort of as if you invented that topic in your math book by yourself. So how do you go about reasoning it out? Is we would like to figure out the volume of this thing by thinking of it as the sum of simpler volumes. And then we're going to do the addition. That addition is called integration. And at this point in this topic, and actually for a lot of engineering purposes, it is not best to think of integration as somehow backwards differentiation. So a lot of calculus books introduce integration as backwards integration. Integration as backwards differentiation. Forget that. Just forget that idea. That's an important idea, but it's actually not the most important thing for most engineering practice. The most important thing about integration is addition. It's something that's sort of you think of in terms of a Riemann sum, which is adding up a bunch of little things to get a big thing. Taking up something and breaking it into little pieces, adding up the little pieces to get the whole. So we'd like to break this into little pieces that we can understand. If we were in Math 192, we could think of this as a volume integral, but because this shape is simple, we don't have to do that. The little pieces can be little pieces that have a little bit of a complicated shape. So what we can do is we can divide this thing into little cylinders of some kind or other. So what we can do is we can say this shape is made up of, and now I can take cylinders here, and let me try to draw a cylinder. So if I come up to some point on this thing, I could draw a cylinder associated with that, and that's something that would go around like so, and come back like that, and it's got an edge like that, and we're interested in that cylinder. So going back to this picture over here, we have a cylinder which is shaped like this. So this is a cylinder. And here it is here, and I'll draw it separately as a cylinder. It's some arc like this. It's got a little slanted side to it. Goes around like that, and it comes down like so. And it's got an inside and an outside. So it's a little cylindrical shell. Okay, so this is a cylindrical shell. Now, if we could figure out the volume of that, then we can maybe think of the volume of the object of interest, which is this whole spherical region, as a sum of these cylinders. At least it's a sum of these cylinders. These are the hard ones. And then it's a sum of this inner cylinder. That's an easy one because the volume of a cylinder is just the base times the height. And then in terms of this original problem back here, we're going to have to add in this thing back here. But the hard part to calculate is this region here. And if we were interested in calculating the whole volume of this half sphere, we would be taking the special case where this h went all the way to the top. Okay. So now how are we going to work this thing out? Well, we're going to draw a picture again. And now we don't have to draw this whole 3D picture every time. We can just draw a 2D picture and keep track of things with the 2D picture. So this 2D picture we're going to draw is this half circle. And we're going to pay attention to a cylinder. Let's say the cylinder is this cylinder here. And we're interested in the volume of this cylinder. And what do we have to work with is that it's got a radius. And now we need to parameterize these cylinders. We're going to look at a whole family of them. This is going to be one cylinder, but we could draw a different cylinder here and a different cylinder here. And we need to keep track of something to label the cylinders. And this is going to be the independent variable in the integration. And what variable we use is our choice. We can use theta, we could use x, we could use y, we can use what we want. Every way we do it, we'll get a legitimate problem. Each one will look like a different calculus problem, but in the end, each one has to give us the same answer for the total volume. So there's not a right way and a wrong way to do it. It's just a matter of choice. And it's a matter of, when we do it, do we get an integral that's easy to solve or hard to solve? One way or another might give us, one way might give us a signed integrator or a cosine, and another one way might give us a square root of 1 minus x squared or something like that, which is not that hard, but it's a little harder looking. Okay, so we parameterize these things as we like. Because there's circles involved, oftentimes it works well to parameterize these things by theta. So here we have an r, we have a theta. What's the height of this thing, of this cylinder that we're trying to add up, is h. What's the radius of this thing? It's going to be a little r. And what is this h? That's r sine theta. What is this r? It's equal to capital R cosine theta. Now, can we figure out the volume of that cylinder? Well, if we want to figure it out exactly, we have to pay attention to exactly what's going on here. And the whole trick of this kind of calculus is that the error we make in not worrying about exactly what's going on up here gets smaller and smaller if we look at narrower and narrower cylinders. Now you could say, oh, the volume of the cylinder gets smaller and smaller, but it's not just that. It's the fractional area, the percent of volume happening up here, divided by the volume of the cylinder goes to 0. So the problem up here gets negligible if we take smaller and smaller slices. And that's the trick that's just used throughout setting up integrals, differential equations, and so on in engineering, is that the little trouble goes away as the whole problem gets smaller. It's not just that the trouble gets smaller in proportion, it gets smaller even faster than that. Because as this gets narrower and narrower, the volume is proportional to the width, but the error here is proportional to the width squared, because it's a little triangle-like thing. So the fractional error goes to 0. Okay, this is a completely confusing point for beginners in this subject, and it's something worth staring and thinking about for every problem you work on, basically, at the beginning. Any quick questions about that? Okay, so now we're going to try and figure out the volume of this little cylindrical slice. So we're going to figure it out by looking at the width of the slice, and I'll call that width delta r. But it's associated with some small angle here, delta theta. So now the question is, what's the relationship between delta theta and delta r? Now we've got this small little triangle is the thing we're worried about. In the end, we are going to try and crowd it out of our lives and say it's so small it doesn't matter. But now we actually have to worry about it. So a common mistake, again, that many of you will make, so I advise you not to make it, is to crowd your confusion into a small picture. So in order to actually understand this little thing we want to worry about, we want to take that little picture and blow it up. And what we have is this arc of a circle, which now looks like a straight line. We have this radial lines coming down here like so. And we have this triangle to worry about. So this is a blow up of that picture. In that picture, we'd like to mark the angle theta. Well, certainly theta is either this angle or that angle. We could work it out very carefully using complementary angles and so on from geometry. But we can just know it's one or the other of those two angles is theta. Which one is it? Let's take the limiting case. If theta is, yes?
Why is it a triangle?
Why is it a triangle? Well, actually, it's not a triangle. Actually, it's a very small arc. But the difference between that arc and a triangle, again, goes to 0 as that triangle gets smaller and smaller. A straight line is a better and better approximation of any curve as you look into a smaller and smaller region. Yes? Where did I get what? These two lines? This is a vertical line. That's this one that's going down here. This is the cylinder that we're interested in. Okay? You happy? Not happy?
I get it.
Do you have a comment?
Confusing.
Still confusing?
Wait, and the hypotenuse is the edge of the circle?
This is
The edge of the sphere, I mean.
this is the edge of the sphere. Let's just stop here. Go ahead, ask.
No. I think it's just confusing because in our calculus classes we think of that shell as being horizontal across, not following the arc. And no, I
First of all-
understand what you're saying. I'm just saying.
Okay, so first of all, there's lots of ways to slice a watermelon, and there's lots of ways to calculate the volume of a sphere, and you can slice it this way or that. When we calculate the volume of this shell, we have a choice about whether to include this triangle region or not. And what I just said to you is it doesn't matter whether we include it or don't include it. So when I drew this picture, it wasn't actually about calculating the volume of this little teensy little lemon peel strip at the top. It was about calculating the relationship between delta theta and delta r. That's what I'm trying to get at here. Because in setting up the sum, I'm trying to pick delta theta as my independent variable. So I need to be able to calculate delta r from delta theta. So that's why I drew this picture. Who follows this picture? Raise your hand. Do not follow the picture? Can you ask a question if you don't follow the picture? What?
For that picture with the semicircle, the 2D one. Yeah, are those shaded regions like sides of the cylinder or are they separate cylinders?
This is a cross section of the sphere, vertical cross section, and when we made that cross section, we picked out a little bit of the cylinder.
So is it the same cylinder though? Like two sides of it?
It's not really two sides of it. If you took a Coke can and cut it like this, you would see the edges of the aluminum, these little strips there. That's what it is. There's a cross section. Okay, so now we're trying to figure out this quantity here, which is this delta R, which is the thickness of the cylinder. We could just call it delta R, the thickness of the cylinder, but we'd like to know it in terms of delta theta because we're going to calculate everything in terms of theta. So we picked in this picture theta as our independent variable, so therefore to set up the integral, we need to be able to calculate everything in terms of theta or delta theta. Okay, so what is this length here? This length here is r delta theta. As I was starting to say, theta somewhere shows up in this triangle. Let's look at the special case when theta is very close to 0. When theta is very close to 0, this thing is very close to vertical. Therefore, this angle must be theta, which I could, as I said, work out by being very careful with complementary angles and so on. So if that angle is theta, I can look at this triangle and I can see this side divided by that side is sine theta. So sine theta is opposite over hypotenuse is delta r over r delta theta. So that then implies that delta r, which is the thickness of the cylinder, is equal to r sine theta delta theta. Okay, so that's our delta R. Now, how high is the cylinder? It's H. So what's this delta V for this little cylinder is equal to the perimeter. That's that circumference multiplied by the height, multiplied by the thickness. So we're trying to find the volume of this cylinder. What is the volume of this? Well, we can unwrap it. When we unwrap it, it's just a rectangular region. And it's a rectangular region, one of whose dimensions is the circumference of the cylinder, one of whose is the height, and one of whose is the thickness. So the volume of this cylindrical piece is the height times the perimeter times the thickness. Now the perimeter is 2 pi this little r. The height is the height. And the thickness is this thing which I just calculated, which is delta r. Now we have ways that we can substitute in for all of these quantities. Delta r, that's the thing we just figured out was r sine theta delta theta. H, that's the thing we figured out over there is r sine theta. And r, this is this radius of this particular slab, is r cosine theta. So substituting those all in, we get that the bit of volume, delta V, is equal to the volume of that cylinder. The volume of the cylinder was the perimeter, which was 2 pi r. And that 2 pi r was a 2 pi r cosine theta. So this part was the perimeter. It's the height, and the height is r sine theta. And it's the thickness. And the thickness is this capital R times sine theta times delta theta. Okay. Now, what I'd like is, especially since you're doing this in Math 191, and especially since this is a skill which, if you have it, will be incredibly useful for you for the rest of the college, to just stare at this for a minute. You would like it to be that if I just totally erase the board, you feel confident that you could reproduce this and get it right, and even not make the algebraic mistakes which I might have made. I don't know. It should not be a mysterious thing. It shouldn't be a thing where you think, I could understand it later if I want to. This is something, if you get this down now, it will really serve you. Well, I'm trying to make the whole course like that. But this is one of those things that it's really a methodology that you'll see again and again, which is trying to calculate the whole by the sum of the parts and then working out what the parts are. Yes?
How do you get R del theta?
How did I get this?
Yeah.
If you look at a circle, the length of perimeter is the radius times the change in angle. Now, where does that come from? That's actually the definition of angle. The most fundamental definition of angle is as the ratio of perimeter to radius.
And why did that become theta?
Why did this become theta?
No, the angle in the triangle.
Why did this angle become theta? Is because I look at this picture here, and I see that when this thing is almost flat, this triangle is almost squeezed there. And then if this triangle is almost up to 90 degrees, this triangle is almost flat like this. So whatever angle this is, it's 0 when theta is 0, and it's pi over 2 when theta is pi over 2. And it smells like we could draw complementary angles and work it out. And this little bit of reasoning always works for the good. So I don't promise you that every single instant in the rest of your life you can fudge this, but probably you can. But if you want me to draw the complementary angles and so on, I can do that. But I'd rather not. Go ahead, you guys try it out loud, because if you're confused, probably somebody else is too.
I was just wondering, like, the cross-section, which cylinder that cross-section?
This cylinder here,
Yeah.
what cylinder is this the cross?
Is like the whole half of the circle, like is that a cross-section of which?
Of which cylinder? Okay, so I've tried to draw here a sphere. And here is a truncated sphere. And what I've done, let me just try the picture like this. I've got Coke and I've got Pepsi. Now it turns out that the Pepsi cans are a millimeter bigger than the Coke cans. And I've got a grapefruit. And I come down the middle and I cut off the bottom of the Coke can, and I come through and I cut out the core of a cylinder, and then I come down with a Pepsi can and I cut out the core again, but I get something bigger. That cylinder in between those two, that's what I'm talking about here. Okay, or another way to do it is I superimpose a Coke can on a grapefruit, and where they overlap, that's what I'm talking about here. Another way to say it is I take this picture here, which is on the plane. Let's say it's on the XZ plane. And I revolve this picture about the Z-axis, and that's the cylinder I'm talking about. Does that work for you, any of those? Go ahead, do it out loud.
I was asking why again is the hypotenuse r delta theta?
Why is the hypotenuse r delta theta? So that comes from this picture here. Here's a radius. Here's a delta theta. That's that same delta theta. And on any circular arc, if we have an arc length here, delta s, and we have an angle here, delta theta, it's always true that delta s is equal to r delta theta. And why is that true? That's the definition of angle, actually. Who asked the question? Are you happy with that? Okay, more. Keep staring at it. You're totally happy with it? 100%? The question is, could you get to that formula by yourself if I erased the whole board? And not just in 1 minute, but an hour or a day from now. So any part that looks fuzzy, ask about. Yes?
What's the benefit of using it as like a function of theta instead of a function of like the radius?
I could have done this whole problem from the beginning, parameterizing by r instead of by theta. I could have done it from the beginning, parameterizing by h instead of r or theta. And all that happens is I'll get a different looking integral. All three are right. All three will give the right answer. It's just a matter of whether you like integrating cosine or sine or the square root of 1 minus x squared or what kinds of... You look at... If you don't like the look of the integral, then you try a different one and maybe you get a nicer looking integral. Yes?
So all you do from here, so after you're left, all you do from there is you basically take the sum of all the cylinders.
Right, so now we're moving on. Ready to move on? All in favor of moving on? Okay, so moving on, what we'd like to say is that the volume is equal to the sum of all the bits of volume. So now this tells us that the region that we're going to get here by adding up these cylinders is a region like this. And if we go from one value of theta to another value of theta, so in this picture, I'll call this theta 1 and I'll call this theta 0, that the volume is equal to the integral from theta 1 to theta 2. And now I have 2 pi as a constant. Capital R is a constant in this integration. In fact, I've carefully made it so that the only variable is theta. Otherwise, the integral would not be a one-dimensional integral. So I have a 2 pi r cubed, which I can take to the outside of the integral. And I have a sine squared theta cosine theta d theta. And this is from theta 1 to theta 2. And that gives the volume of what is the volume of that thing over there. Now, if I want to know the total volume of interest, I have to add back in the cylinder. So if I want to get the total volume of the sphere up to the point of interest, the total volume is going to be that V plus the volume of the cylinder, which is a pi times the radius of that cylinder. What's the radius of that cylinder? It's r cosine, I'll get your question in a minute, theta 2. That's the radius of that cylinder squared times the height of that cylinder, which is r sine theta 2. And then I have to also add back in the bottom of the sphere, which is 2/3 pi capital R cubed. So this is the total volume that you needed for the homework problem, is the volume we're calculating here using calculus plus these two missing pieces. Now, what was your question? Say again?
Theta 2. What is it?
Theta 2 is telling us where we've truncated the top of the picture. So we were interested, remember, in knowing what happens for what's the volume of a sphere truncated at h, and we've got h is equal to r sine theta 2. So it's the upper limit of integration for calculating this volume. Okay, now this is an integral you can do, and I'm going to skip it. That's u squared du, which is the integral of u cubed over 3, and you can do it. Yes?
2/3 pi r cubed, is that because it's the other half of the circle?
The other half of the sphere, right.
What about the section up top?
So we've got this part goes to this part in here. And we've got this part over here, which corresponds to the missing cylinder in the middle, which is just a solid, regular old right solid cylinder.
What about?
That part, we don't want it.
Okay.
That's where we're going. We could have just remembered 4/3 pi r cubed. Now, if we did want it, what do? Let's say we want to know the volume of a sphere. What would happen to this calculation? We would set theta 2 equal to pi over 2. This volume would disappear, and we get the volume of a sphere. Yes?
How do you get the bottom of 2/3 pi r cubed?
How did I get it? I just remember that the volume of a sphere is 4/3 pi r cubed. And so this is half of a sphere, 2/3 pi r cubed. But if I didn't remember it, I'd be all set. Because what could I do? I could just use my calculation here, which is going to give us the right answer. Use it with theta 2 equals pi over 2. And that gives me the volume of the bottom half of the sphere. I'll get that from this integral. Yes?
Is theta 1 and theta 2 corresponding to theta 1 and theta 0, or is theta 2?
Oh, I called it theta 0. This is a typo.
Okay, so it's not 0.
Whatever, 1, 0, the lower one. Yes?
Is it supposed to be cosine theta squared, or
Is it supposed to be a cosine?
we have it cosine theta squared? It's sine squared.
Where do I have cosine theta squared? That looks good to me. This is the volume of this cylinder. What's the volume of this cylinder? It's the basal area times the height. The basal area is r cosine theta squared. pi r squared times the height.
But if we've calculated V, why do we need the volume of the cylinder?
The volume we've calculated is just the volume of this region here. We've only added up these shells. That's the only integral we set up. We added up all these cylindrical shells from here to here. Go ahead, do it out loud.
I was just saying the integral is going to be sensitive. I was just calculating the integral.
The integral's easy, right? It's u squared du. Go ahead, out loud.
How did you get the volume of the middle portion as pi into r, whatever it is?
How did I get the volume of this portion here? This portion is a right cylinder. A right cylinder means a regular old-fashioned cylinder. The volume of a regular old-fashioned cylinder is the area of the base times the height. The area of the base is the area of a circle. The radius of the circular base is r cosine theta 2. Take that radius squared, multiply it by the height, r sine theta gives us the volume of that little region. Anything else? Yes?
Wait, the 2/3 pi r cubed, that's the bottom half, like, is that supposed to be a cylinder?
The bottom half is a sphere.
Yeah. So,
Half a sphere.
oh, that's just the bottom sphere.
Yeah. Yes?
Where's theta 2 in the picture? I understand how you got it, but I don't.
Here's theta 2 in this picture. It's not the cylinder of interest, which is associated with some other theta. It's the biggest cylinder, the tallest cylinder we're going to look at in the integration. Who asked the question? Is that good enough for you? In this picture, we're going to truncate this thing up here someplace, and we're only going to look between here and here, and this would be theta 2. Now could you do the whole thing yourself? Who could do the whole thing themselves tomorrow without looking at the board or any notes? Raise your hand. Okay, not good enough. So keep asking questions.
Using this method?
Using this method, right. What's another method? I mean, if you did another method like parameterized by R or parameterized by H, or do it with disks instead of cylinders, you have to go through exactly the same steps. Each little bit of the geometry will be different, but you have to go through exactly the same steps. So it should be that you feel confident not only could you do this, but you could do it with R, you could do it with H also. Yes?
We're looking for the part of the sphere that's submerged in oil, right? That is lifted up into the oil.
This is... The calculation that I'm interested in here, actually, is just this volume here. This is the hard part. What we're interested in back for the original... Who asked the question? Original buoyancy question was the volume of some whole bit of sphere that includes a whole half plus a little bit. So this was the part, this is an upside down picture of the part that was in the oil. And this is the part that's in the milk. Now I could have done this calculation differently. I could have gone from here out and then done a different subtraction. Yes?
If you know the radius of the sphere to, like, say, take out the, like, when you have, it's kind of hard for me to say this, but like when you have that line on the top,
Yeah.
you draw those two vertical lines downward,
Yes.
and then you imagine that whole cylinder taken out because you can calculate it easily.
Yes.
Wouldn't it be easier to do the integral from the radius of the sphere minus the radius of the cylinder, and then...
So we could parameterize the integral by taking shells.
And then double that?
We don't even have to double it. We could say we're going to describe everything in terms of the radius, and then we have a dr, but then we have to calculate the height in terms of the radius. So we're going to have a square root of r squared minus the radius squared for the height. And if you like square roots better than sines and cosines, and that's fine. But it's not, I would say overall that's a little bit messier, but it's basically equivalent. Yes? Are you happy with that? Okay, now, I'm still want it to be that you, I think I'm not going to go any further than this in this class. So for 4 minutes, we're going to do this. I'm going to do 1 minute intro to the lab, and then I'm going to actually pick this up next class, because what I want to do, where I want to go with this, is that most often in engineering practice, when you get to this stage, you don't get to an integral you could recognize and can do. You get to an integral you can't do. So the question is, if you get to an integral you can't do, and not only that, you can't find it in the back of the book, and not only that, your symbolic calculator doesn't know the answer, then you have to calculate it numerically. What I wanted to show you is how to do this numerically. So I will do that next class. So for 2 more minutes, I want to answer questions about just the setup of this. Then 1 minute on the lab, and next class I'll do the numerical integration. Yes?
Essentially, the volume of the sphere that we're not calculating, what part is that? Like,
if we wanted to use this calculation to calculate the volume of a sphere, how would we use it? We would set theta 2 equal to pi over 2. And then if we said we didn't want to calculate the volume of the sphere by already knowing the answer, we would leave this term off and then multiply by 2.
so what are we doing with this? Like, what is like this formula exactly? Like,
What this formula is exactly is the volume of a sphere that's been cut off at height h. Yes? Go ahead. Those of you who are chatting to each other, try to do it out loud. People who are asking each other questions, try to do it out loud, because mostly other people will benefit. Yes?
So in the end, we're looking for the change in R, right? Like, because we wanted to know how far up or down the sphere went in the milk. So wouldn't we eventually want our answer in terms of, the distance R or the distance h from the center of the sphere to the top of the area?
Right. So we've now parameterized this volume in terms of theta 2,
right,
not in terms of h.
Yeah.
So if we wanted to turn this into a formula in terms of h, so we could plug it back into the oil and milk problem, every place we see a theta 2 here, we have to put what? Arc sine of h over capital R.
Right. So, but that would then give you the height.
So theta 2 is arc sine of capital H over R. So that'll give us the volume submerged in terms of capital H. Yes?
Why don't you need a 2 being the final equation, because you have to include both sides?
I've only actually, the integral here, which was the part that we were interested in, only calculates the volume of this little quadrant here. When we set up this whole integral, all we set up was the volume of this weird slice.
But then you rotate that around, so you end up getting the whole outside.
You get the whole outside, but not the bottom half of it. So we got the left and right, but we didn't get the top and bottom. But again, there are lots of ways you could slice this. We could take the top and bottom, then we'd have a factor of 2 here. We could calculate this cylinder here. Then we'd have to worry about this cap. Go ahead. Question?
I'm just confused about, because looking at the first picture we drew, with it's not on the board anymore, where the ball went up in the water.
Yes. This whole picture is an upside down of that picture. So right at the very beginning I said I'm going to flip it because it's easier to draw it right side up. Okay. I really recommend that you, how many people look at the videos for this course? How many people find them useful? So. Anyhow, nail this. Understand it inside and out. It will help you for your 191 exam, I promise. It will help you for the rest of your life, I promise. Be able to do this problem. If you don't like this way of doing it, understand it anyway, and then do it your way too, and then understand both ways and see how they compare. Okay, about the lab. 1 minute about the lab. Who knows the TV show MacGyver? Okay, so MacGyver, wherever he is, he figures out how to do things with paper clips and so on. Today, you're given a real valve, like the kind of thing you buy in a hardware store, and you're given your Lego robot kit, and you've got to make the Lego robot kit control this real physical valve. And there's not like a Lego part that says control valve. So you're going to use tape and anything else you can find around, and just, this is going to be real in the dirt engineering. Take Lego and make it control a real valve, and then you're going to do a little control problem. Okay.